All right, recorded is rolling. So it's Thursday, February 16th. Forget to mention yesterday, there's a faculty meeting. They said they're gonna ban cell phones on campus, especially starting at 227, which is about a week from now. You guys probably heard that from your other teachers too. So yeah, I know I have guys sometimes use cell phones for different things in class, like stopwatch functions and stuff, but they want you guys to instead use the laptops they give you a few weeks back. So anyway, it's from the district. Whole school's gonna do this stuff. There we go. Right. You guys got your dynamics quizzes back. The solutions I just posted this morning. And we're gonna do these other things day 2. So you guys remember yesterday I opened up some AP class questions. I gave you guys a quarter page yesterday. You guys remember that? Wrote your name on it, numbered it 1 through 11. Okay. If you lost that, then just take out another piece of paper because I'm gonna pick that up by the end of class to give you guys points for that. You guys remember Unit 3 on AP Classroom? Have that turn in by Monday morning so that we can go over that Monday. And look at all the stuff I want to do for a review for Unit 3. Let's bump the quiz back a day to Wednesday, just so you can put like an extra part to at least. Okay. All right, so let's look at this dynamics review quiz. Okay, so now that everybody's done this, then give it back to you guys. I just want to hit. There were at least a couple of questions that I want to take an extra look at. All right, so one of them was this one here. It's Atwood. Right now, you guys know Atwood pop up all over the place in AP Physics, right? So you guys did a couple of labs on Atwoods. And in the review, whatever. Okay, what's the acceleration of the system? The downward acceleration of the large block, the upward acceleration of the small block, and also what's the tension of the string? Like you should be able to calculate each of those, and then also be ready to field a question from AP, something like, well, if you increase the mass of this block, how does that affect the acceleration of the system or the tension or something like that? Okay, and remember, you can always make up. If you ever get a question like that from AP, you can always just make up numbers and test it out and see what happens, right? Okay. I gave you guys a shortcut trick to think about the tension in the string. I told you guys here, wouldn't it have to be the case that the large block has a net force downward and the small block has a net force upward? That's to say that the tension has to be smaller magnitude than the weight of the large one, but also larger magnitude than the weight of the small one. Wouldn't that be true? Okay. So a quick way you can get the answer to this question it is here. If you look at the two masses, like this one says 5 kilograms and 6 kilograms. I know everybody has a different paper, okay? But wouldn't this have a weight of 50 newtons? This has a weight of 60 newtons. So wouldn't it make sense that the tension has to be somewhere between those two? Right? So I might start at 55 newtons. Actually, it has to be a little bit less than that. But actually, that from there, like just from the multiple choice answers I gave you, there's only one choice that even fits within that window, right? And that was actually true for most of the versions. So you could just get it just from doing that trick, right? So I bet if you ran the numbers on this, it would come out to the 54 point something. It probably rounded up to 55. Okay. So that was one of them. All right. So a couple of other ones on the back. So there was this modified Atwood. And I was saying, if you change mass 1, then how does that affect the horizontal acceleration of M2, or you can think the acceleration just in general? Okay. I didn't specify whether there was friction or not, but that turns out to be irrelevant whether you think there's friction or not. Okay. So let's put this together. So we're looking for what's the acceleration as a function of M1, right? And here, I got those solutions right here. They break this out. Could you guys come up with, this is from a macroscopic way of thinking of it, Newton's second law of motion. The acceleration would be the net force divided by the total mass, right? And there's only one force, if you exclude friction, there's only one force that really matters. What is that one force? The weight of M1, right? M1G, right? Now, if there was friction, you could also subtract that off. It's going to slow it down a little bit, but that doesn't actually affect the particular answer. Right? So in a frictionless case, this would be true. It'd be this weight acting on this much inertia, right? This much mass, right? So what happens as you increase M1? Well, what if M1 is equal to 0? That's to say, like, what if you just have a string hanging out over the end? Guys, if it's just a string hanging out over the end, what's the acceleration? 0. It's not moving at all, right? Okay, so one point that you know it has to exist is 0, 0. If M1 is 0, then the acceleration has to be 0, which might be this one or it might be this one, but it couldn't be either one of these. Right? And then as you start to increase M1, Hey, what about this? What if the two blocks are the same mass? And let's also ignore friction. Just right. If the blocks are the same mass, like let's say 1 kilogram and 1 kilogram, could this be 10 newtons acting on 10 newtons acting on 2 kilograms, which would be like 5 meters per second squared, which would be half the rate of free fall, right? Okay, so now we do have some acceleration. We have half the rate of free fall, right? What if M1 is significantly larger than M2? Like, what if this is like 10 kilograms to 1 kilogram? Ooh, aren't we approaching a case where it's just getting closer and closer to free fall, right? What if it's 100 kilograms to 1 kilogram, right? Now it would be almost pure free fall, right? Right. What if it's 100 kilograms compared to like a paperclip, right? Okay. So do you guys see it has to asymptotically approach free fall? Right. That's why the answer is this one right here. Okay. Now, if you picked this one, you may have been thinking, because almost all the time in this class, acceleration versus time comes out to be a flat line. That's also called uniform acceleration. If you're talking about acceleration versus time, but that's not what these graphs are. These graphs for acceleration is a function of the mass M1. Okay, so it has to asymptotically approach free fall. Okay. Okay. Another one, you guys struggle with the ball bouncing off the ceiling, which was also a question on the previous quiz, right? Kinematic motion, I asked you guys something about a ball bouncing off the ceiling, acceleration versus time, and now we're looking at free body diagram. So if you got the last one, well, you'd have to get this one because it's the same question, just just in terms of forces now. Okay. So the answer was there are two forces acting on the ball when it's bouncing off the ceiling. Okay? Its own weight is pulling it straight down, but also there's a normal force from the ceiling pushing it down because it's bouncing off the ceiling. So it has to be this one right here, right? Some of these I threw in like a throwing force, but the throwing force only counts while you're throwing it. As soon as it leaves your hand, that force is gone, right? So yeah, so there's only two forces: the weight and the normal force from the ceiling. You know what? While I've got this out, let's take a quick look at the train because I told you guys there were some of these chain gang type questions coming up. I gave you guys the force from the engine. Now the engine has to drive all this mass, which is like 4,000 kilograms. So Newton's second law of motion, that force divided by this total mass will give you the acceleration of the train system. So many meters per second squared. Okay. And then the follow-up question was, I labeled this tension force right here, this F sub T. I said, well, what's the tension specifically in that? And we went over this in the review, and you guys saw a bunch of AP classroom questions. We said, okay, the maximum tension would have to be this one, and then this would be less tension and less tension. Because all these train cars have the same acceleration, but each of these cables is pulling less and less mass behind it, right? So this last cable is only pulling one car. It's only pulling 1,000 kilograms. So you can just do F equals ma. You can say whatever this force is, which you're solving for, is this mass, which is being accelerated, times the known acceleration, which was the answer to the previous question. Okay? All right, you guys got that? Okay, so again, I posted all the solutions. These are them right here. So if you want to open up that file and take another look at that, those are on Google Classroom. And then if you want to do correctness and turn those in, then I'll give you guys fresh credit back. All right, let's look at these gravitation questions. So I'm going to switch my laptop over.